So, today we are looking at lesson 10.2, Comparing Two Means. And in this section we will learn to compare the means from two populations or two treatment groups. And here we are looking at both confidence intervals and significance tests. So, the condition here is that we are looking at, for instance, two separate SRSs from two distinct populations. And so we'd have population 1 and population 2, and they would each have their own mean. And our goal is either to find a C-level confidence interval to estimate a difference in the mean from two populations, or to perform a hypothesis test for the difference in two population parameters. And of course, the type of, there could be three different hypothesis tests that you could do. So if we first said that our null hypothesis was the difference, so we could choose mu A minus mu B. And of course, it's very important when you're doing the differences that you choose which one you're subtracting from the other. So usually, the null hypothesis is that the difference is 0. Or you could write that as mu A equals mu B. That's usually our null hypothesis. And if that is the case, then one alternative hypothesis would be that the mean for A was greater than the mean for B, or the mean for A is less than the mean for B, or the mean for A, the two-sided test is that the mean for A is not equal to the mean for B. So if we had written it as mu A minus mu B equals 0, then this would be mu A minus mu B is less than 0. Mu A up here, mu A minus mu B is greater than 0. And of course, mu A minus mu B two-sided is not equal to 0. All right. So, conditions for comparing two samples. Once again, for random, we have two SRSs from two different populations. Or random assignment if there's an experiment of treatments. Random assignment of treatments. Independent The samples are independent from each other. And this should be the case if we have two independent populations. And each one should follow the 10% condition if sampling without replacement. So each one. And of course, independence between all observations. And our last condition is, of course, normal. First of all, we could have that the underlying populations are normal. And then our difference would be normal as well. Or we could have the central limit theorem telling us that n must be greater than or equal to 30 for each sample. Or, in practice, the populations have similar distributions. And that there are no outliers. So let's just review our notation for our two samples. If we have populations 1 and 2, the variable will be x1 and x2. The mean will be mu1 and mu2. The standard deviation is sigma 1 and sigma 2. That's for the population itself. And the variable. Let's continue on. The sample size will be n1 and n2. The sample mean will be x1 bar, x2 bar, and the sample standard deviation is s1 and s2. So for the sampling distribution of x1 and x2, we will start, I'm just going to start, we'll do this here and continue on up. So if conditions are met, so that's random, independent, and normal, the sampling distribution will be normal. And the mean of the difference of the sample means, so x1 bar minus x2 bar, will be an unbiased estimator of the difference in the population means. So in other words, mu1 minus mu2. So we'll just continue on up here. In that case, we can use x1 bar, the difference of the sample means, to estimate the difference of the population means. Okay, now that tells us about the mean of our sampling distribution. Now we need to look at the spread. And you will recall, once again, that when we dealt with random variables, the variance of, when we take the difference, it's the variance that we have to deal with, not the standard deviation directly. And so for a difference, the variance is the sum of the variances. So the variance of the sample means is sigma 1 squared over n1 plus sigma 2 squared over n2. So then we end up with a two-sample test statistic. So that gives us, first of all, the standard deviation. It will become now the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay? So that's the standard deviation. And so we get a two-sample test statistic for a z-test. Where the population standard deviation is known. And in your textbook there is an example of this where we know the mean height and standard deviation for girls of a certain age and the same for boys of the same age, and we can do a test on whether the mean height for boys is greater than the mean height for girls. And in that case, we know their standard deviations. So here is what our z-test looks like. It's x, the difference, the sample difference, the difference in the sample means minus the difference in the population means divided by sigma 1 squared over n1 plus sigma 2 squared over n2. Now, once again, that's when our standard deviation is known. Most often, of course, we don't know our standard deviation when we're doing experiments or studies. And so, of course, we end up using our two-sample t-procedures when we do